This video is on the mysterious component in the grounded grid amplifier circuit. There's a lot of confusion about this grounded grid thing and a lot of incorrect information online, such as the fable that the input power is not lost because it's transferred to the output. If you look at it from an RF perspective, that's absolutely false because a 50 ohm source cannot transfer power to a 2500 ohm plate. And on this page, he explains where that myth came from. It came from the FCC. But here is W8JI, and W8JI was an engineer for IMAC apparently. Circuit of a grounded grid amplifier. On the far left, you got the exciter source, 2 megahertz. You got L4, C6, C7, which is a matching network. You got a coupling capacitor, low reactance, a small series resistance on each side. Those are current limiters. And 100 microhenry choke to ground. That's not a tremendous amount of inductance, is it? And the grid, both the grids are effectively grounded. The screen grid's grounded, and the control grid goes down to a 5-volt source. Now, in modern zero bias triodes, there's no grid voltage source. That 5-volt B2 down there is what gives away the gross mistake in this kind of circuit. See the 6L6 V1? That's a receiving tube. And this is the old kind of grounded grid circuit. This used receiving tubes. And although the 6L6 is used as an RF final in amateur service, it's still a receiving tube because it was used in television receivers. But the characteristic of receiving tubes is that when the grid, the control grid, pardon me, when the control grid is at 0 volts, the plate current runs away because the control grid works by having a negative bias and repelling electrons from the cathode from reaching the anode. So the 5-volt source there is to back bias. Notice the negative top of B2 is at the grid and the positive is at ground, so that's minus 5-volt bias. And that's generally cut off for a small receiving tube. Now on the RF final amps and our old transmitters, that would be about 50 to 60 volts. But the magnitude's not what's relevant. The grid G1 is minus, so the tube's cut off. Now the contradiction comes over here at the load, which is referenced incorrectly to the earth ground symbol. That should be a chassis ground symbol. Should be a three-pronged rake. But R3, C4, C3, C5, and B1, the plate voltage or plate cathode voltage, are all referenced to chassis ground. So is the control grid. Imagine it's a zero bias tube and B2 is not there. It's just grounded grid. And that's what the modern power grid triodes are. They're just simply, the grid is simply grounded to the chassis. Everything over here is grounded. The problem is that B1 must be connected to the cathode. B1 cannot be connected to the grid because the grid will be instantly destroyed. The heater provides the energy to loosen the electrons on the cathode on the left of the tube, and B1 supplies the electric current to cause current to flow from the cathode on the left to the plate on the right through the grids. The B1 supply cannot be grounded to the grid or the grid will be vaporized. Now we have a problem. If we take the ground symbol from B1 at the bottom there and take it over here to the cathode, now the cathode is shorted to the grid and the input signal, which is across the cathode and grid, is shorted, so there's no drive. Open that connection up and there's exciter RF potential across grid to cathode, so that's good. But it's an open circuit on the plate power supply, so there's no output. So here's the paradox I've been beating my head against the wall trying to figure out, and no one has done a thorough job of explaining it. And I figured that it all boiled down to that inductor, but nobody has explained how to calculate the exact value of that inductor. And this is electronic RF engineering. It's not guessing. We don't guess at these things. We don't guess at 16.41 microhenry. It's calculated. This circuit won't work without L1. The entire operation of this circuit hangs on L1, but there's no explanation of what L1 does. Obviously, it's in between the condition of an open between the plate supply and a short to the plate supply, but that's not enough description. So down the page here, we have a gross mistake. Ground to grid amplifier power efficiency measurements. The input and output of the ground to grid amplifier connected in series through the tube. Plate current is common through both cathode and anode, and only DC plate voltage is not. That is false. DC plate voltage is applied to the cathode from B1 ground up through L1. Realize during steady state DC, an inductor disappears and gets replaced with its winding resistance. So the DC power supply is across plate to cathode. So you got to be aware these ham documents are loaded with mistakes. This is a problem with having engineers that are experienced these kind of things, and I know because I've done this, trying to write technical documents for others. It's usually a disaster. It's a mistake to get an engineer to write a technical or a work instruction document, because it's too easy for someone like this to mentally supply what he knows that's missing in a document, and he doesn't realize it's missing because he already knows it. Down here, ground to grid tetrode general example is where the explanation of what that inductor does comes, but it's hidden and it's not well explained. And here shows a paradox of the high voltage supplies on the left having to be connected to the cathode, but it has to be through the inductor because that inductor is what makes the AC swing appear between the cathode and the grid, G1. And you can read about that in here. But the key to this is hidden down here in this section, distortion and gain reducing negative feedback. All plate and screen current flows through L1 in the cathode system. There's L1. That contradicts the above statement that there's no DC path to the cathode. If we have an effective time-varying signal RF anode current of 1 amp, the generator source would have to also have 1 amp of RMS current to counteract that current. That's poorly stated. What it means here is that they're the same current. What's happening here is that the exciter, the source minus 50 volts, in the power grid tube, and not necessarily in this example, is causing a current between the cathode and the grid. This is why the grid in the power grid tube has to be able to dissipate 20 watts. That's in series with the cathode to plate current, so the two currents have to be the same. And there's what's missing from these descriptions. And it's stated here, but not very clearly. This is the current varying through the RF cycle, not the steady or average indicated DC plate current. And it goes on to say the driving resistance, how that's figured. Well, it's the voltage swing necessary to make the grid to cathode operate times the plate current, because the plate current has to be the same as the exciter current because they're in series. In contrast to a grounded cathode, where when the cathode's grounded and the grid is the so-called driven terminal, the exciter is across grid to cathode and the plate supply and the output circuit is across plate to cathode, so they're somewhat in parallel. Grid current then can flow somewhat independent of the plate current, but here in the grounded grid, the input current and the RF, now this is RF input current and the RF plate current must be the same value. And think of it as the current in between the grid and the cathode on the left being the same electron stream as what travels to the plate. So they have to be the same value. And here's the happy Amprex 3-400 that I got. Cheap, brand new, the old stock 3-400 grounded grid tube. 8163, still in the box, never used. So that's going in the tube tester. But here's the filament transformer from the 4-1000 amplifier I got from Ralph Lockhart, the 4kW amplifier that was in his basement, driven by the 300-pound power supply, which was a 10 kV transformer. But here's a circuit typical for those power tube amplifiers of 30 or 40 years ago. Here's a typical schematic for that transformer, and B minus, the negative side of the high voltage supply connection, always goes to the center tap of that transformer. And then the secondary of the transformer goes to the filament and or the cathode leads for the filament. But the fact there's a B minus connection there also means that the cathode is trying to go to B minus, but it can't go directly because it was short across grid to cathode. And this is what threw me for a loop. How can B minus couple RF current through the transformer? Well, it has to. And I didn't stop to realize the turns ratio. This is a 120 volt input, or maybe 240. But the output is 6.5 volts AC, which is essentially 5 volts AC for the tube. That's a tremendous step-down ratio, and the step-down to the output current of 22 or 25 or 30-some amp means that secondary winding is very heavy gauge wire and not very many turns. So it's a lower impedance to the AC signal being drawn from the B minus supply. So it's actually drawing current from the high voltage supply into the cathode, contrary to the mistake on WHI's website. Because again, the high voltage supply absolutely must be tied to the cathode or the tube cannot work. That's the first rule of tubes. The plate voltage is referenced to the cathode. So what's required here is a reactance in the cathode between the high voltage supply and the cathode that won't short the input driving signal, but will also allow a relatively low impedance path from the high voltage supply where the two currents are the same. It's the same current. Now this brings a question. The two goals of a modern grounded grid are to have the grid grounded to basically knock out the Miller capacitance, the capacitance between the elements and tubes that tends to cause oscillation. I only plan to operate this amplifier on 80 meters. I don't worry about parasitic oscillations. That chance that's going to be pretty low. Or I'm sorry, it's about neutralization, not needing neutralized, which is normally needed in a grounded cathode. Neutralization is needed to prevent parasitics. So the grounded grid is at lower frequencies used to eliminate neutralization. But the other thing in these modern tubes is that they are zero bias tubes. In the old circuit, like I showed you, let's see where to go here. Trying to operate that tube, that old receive tube at zero bias will burn the grid up, will burn the plate up. Because with zero bias on the grid, the plate current is maximum. But these modern power grid tubes are zero bias. This is called a zero bias triode. Here, filament to grid voltage, where filament is the cathode, here's 0. 0 volts filament to cathode. And I've tested this. Follow the 0 volt line over here to where most amateur amplifiers run, 2,000 to 3,000 volts. The ideal is 1,500. But we follow over here, it's about halfway between these first two lines, and that's between 0 and 100 milliamp, and that's plate current. That's idle. So that tube can sit there, and I have tested this in a tube tester. The tube can sit there. It's a triode. There's no screen, no voltage on the grid, and just a little bit of idle current from the plate from the cathode to the plate. So no bias. So I don't care about neutralization. It's easy to neutralize an amplifier. Why not just do this? Why not kill this phone for refusing to focus? Maybe it needs a trip down the steps. Why not connect it just like a regular grounded cathode circuit? The grid to cathode doesn't know and doesn't care which way around the exciter is connected. All it knows is that when the grid goes plus, the plate current goes up. That eliminates all this nonsense. And again, I don't care about neutralization, it's low frequency. I can sweep the output of the amplifier backwards, and I can find out if there are any parasitic resonances. That's easy. And I can make traps to trap that out. Trivial problem. So all I care about is one of the main benefits of the grounded grid, and that's eliminating the high voltage screen supply, 500 volts, and eliminating the upwards of 100-volt grid supply. This grounded grid eliminates 2 supply voltages. Well, no, it's not grounded grid that does that. It's zero bias that does that. And this 8163 is a zero bias triode. So there should be no reason why it can't be connected like this, like the ordinary grounded cathode, and just feed the RF with the input coax ground to the cathode, like in a common cathode, RF to the grid through a matching network, because the exciter's 50 ohms these days. Put the high voltage plate the cathode where it's supposed to be. There's no need to ground the grid. I'll find any parasitics before I fire it up. But again, I'm not needing a higher voltage grid supply and a high voltage dangerous screen grid supply because it's a triode. And since it's a zero bias triode, there's no need for a grid DC power supply to bias the grid to cathode for the exciter to swing back against. So this is how I'm going to actually put this tube in a tube tester and run it through test before applying RF to it. But that should work, and I've never seen this done. So I get it that we might want to try to get both benefits of grounded grid, a simple circuit. Well, the simple circuit's because it's a zero bias triode, but also a lack of neutralization. We don't need much neutralization at 3.5 megahertz. So that should not be a problem. So that's what I'm going to do. So there's the paradox with grounded grid. And embarrassingly enough, it took me several years of largely doing other things to figure this riddle out, because again, the information online is either so full of errors or so vague that nobody explains this.